Welcome to Kinematics Graphs. As always, if you enjoy this content, give us a like and subscribe. Kinematics graphs can be tricky. The key to understanding kinematics graphs is understanding the relationship between slope and the kinematics quantities and the area and the kinematics quantities. So we really need to start with the definition of slope. And slope is defined as change in y over change in x. So if we have a graph like this, and we have our y-axis and our x-axis, and let's say we have a graph that looks like that. If we pick a couple of points on that graph, this is going to be our y2 and our y1. So change is y2 minus y1, and that would be our change in y. If we follow this graph down, these points, then we have our x2 minus our x1, which gives us our delta x. And that's the slope of this line. That's going to be true for any graph. When we get into the kinematics graph specifically, this will be replaced by distance, velocity, or acceleration. So let's look at a couple of other examples of slope. So let's say again we have a y and an x, and we have a line here that is not changing y. Y is not changing. So therefore our slope is 0. What if we have something, for example, like this? So now the slope is the tangent line at any single point. So if we look at the slope right here, the slope is actually relatively low. But as time is going on, the slope is getting steeper. You could think of this as hiking up a mountain. What's happening to the steepness of the slope that you're hiking? It's getting steeper, so the slope is increasing. So the opposite of that would be a slope that is decreasing. So again, if you're hiking up, although you're going higher, the steepness is getting less. So this would be a decreasing slope. Okay, what about area? There are two formulas for area. For a triangle, right triangle, the area is equal to 1/2 base times the height. And for a rectangle, the formula is area equals length times width, or in a lot of cases, we'll be doing height times width. But we can look at it either way. It's going to be the same thing. So let's say, for example, we come back here and we have a graph. The area that is underneath this line forms a triangle. So we would use 1/2 the base. So the base would be 0 to whatever this x value is, times the height, which would be this right here. And that's the area under the graph. For a rectangle, we can say this is the length and this is the width. So we have our y and our x, and our area would be length times width. Or you can use height. Either way, it's the same thing. In a more complicated graph, where maybe we had something like this, and then comes down like that. This is our y, this is our x. Then we would have two triangles and a rectangle. So we would find the area of this, and we would find the area of this, and we'd find the area of this, and we would add them together. Lastly, what if we have a graph that goes below the x-axis? So let's say we have something like this. And that's our x-axis. This would be positive area, and this would be negative area. So if these ended up equal each other, it would be 0. But let's say this was plus 4 and this was minus 3, then we would be left with plus 1. Let's take our understanding of slope and apply it to the quantities in kinematics. So we know that slope is equal to change in y over change in x. So if we take a graph that is d over t, then what we can do is say that d divided by t is the slope. Well, we also know that d divided by t is velocity. So if we were to find the slope of this line, we're finding d divided by t, so we're finding v. So the slope of a displacement time graph is equal to the velocity. Now, in the different questions that we're going to be doing, d could be displacement, which is what I wish they would always do, because that's technically what it should be. Distance, which means we don't have to take into account the direction, because it's a scalar, or sometimes they'll use position. In other words, saying where it is. But all three of these can be used on this axis, and when we're dealing with the slope of any of these three with respect to time, we're talking about velocity. So the key idea here is that the slope of a displacement time graph is velocity. So let's look at the different slopes that we could have. In this one, the slope is constant. The steepness of the slope is not changing, so the velocity is constant. This would represent a constant slope, but it's negative, so it's a negative velocity, meaning it's moving in the negative direction. That could be left or it could be down. In this case, I have to label my axes. In this case, the slope is increasing. The steepness of the line is going up. Since the slope is the distance divided by time, it's the velocity. If the slope is increasing, the velocity is increasing. In a graph that looks like this, again, the key idea is that the slope of a displacement time graph is velocity. So whatever the slope does, that informs us about the velocity. That's crucial to understanding this. So what's happening to the slope? What's happening to the steepness? The steepness is decreasing. So if the steepness is decreasing, then the velocity is decreasing. One other thing that we can look at here is that the steepness of the line tells us the magnitude of the velocity. So the steeper the line, the greater the velocity. All three of these are constant velocity, but this one is the fastest. And lastly, the simplest one would just be a horizontal line. What's the steepness of this line? It has no steepness. It has no slope. The slope is 0. So therefore, the velocity is 0. But we have to be careful with this because it could be stopped in many different locations. It could be stopped here. It could be stopped here. It could even be stopped somewhere along the negative axis. We know now that the slope of a distance versus time graph is velocity. But what if we do the slope of a velocity time graph? In this case, we're now dividing v by t. So the slope is v over t. Now, technically, if we have a line like this and we pick some points, we're dealing with the change in v and the change in t. So what is the slope equal to of the change in v over the change in t? And we know that that formula is the acceleration. So the slope of this line is constant, so therefore our acceleration is constant. It's the same idea, and this is crucial. The slope of a distance time graph is velocity. The slope of a velocity time graph is acceleration. So whatever the slope is on this graph, that informs us about the acceleration. So let's look at a couple of different examples. What if we have a graph like this, where the graph is on the x-axis? Well, that would tell us that the velocity is 0. In other words, the object is not moving. Well, if the object is not moving, it can't be accelerating. So what's the slope of a horizontal line? It has no steepness, so its acceleration is 0. Its slope is 0. But what if we have this? What if the velocity looks like that? This would be a constant velocity, and the slope is 0, so the acceleration is 0. How does that differ from this graph? This is an object that is stopped, so it's not accelerating. This is an object that's at a constant velocity, so it's not accelerating. These two situations are considered to be in equilibrium. Okay, what about this graph? I'll move this t over. So this graph is a little bit tricky. What it's saying is we start with a positive velocity, and that velocity decreases to 0. So what happens when it gets to 0? It stops. Then it starts to increase. Remember that in physics, -6 is just as large as +6. The negative sign doesn't mean less, it just means in the opposite direction. So this object has slowed down, then sped up. The slope of a velocity time graph is acceleration, and in this case, it's a constant acceleration but a negative slope. So it's a negative constant value. We're going to see that later in Freefall. This is the graph for a ball thrown straight up in the air that then comes back down. Now we need to talk about area. But before we talk about area, let's just review. Remember that the slope of a distance time graph is the velocity. And when I say distance, that could be displacement or position. And that the slope of a velocity time graph is acceleration. Well, then what's the area? So if we take a look at a graph, and let's pick an acceleration time graph, and let's say we have a constant acceleration. If we choose an area within that, we can say that this area is going to be equal to the acceleration here, because that's the height of our graph, and the time here, which is going to be the width of our graph. So the acceleration times the time is going to be equal to the area. Well, don't we know that acceleration is equal to change in velocity over time? So if we cross multiply a times t is equal to the change in velocity. But right up here we said a times t is equal to the area, so that's going to be equal to the area. So what's the area equal to? It's equal to the change in velocity. The slope of a displacement time graph is velocity. The slope of a velocity time graph is acceleration. The area under the graph of an acceleration time graph is the change in velocity. Now, we can look at this also for a velocity time graph. So this time I'm going to pick a diagonal line so that we can see that in this case it's actually a triangle. And let's say we have V and T. So we know in the same way as before the velocity times the time is going to be equal to the area. So we recall that velocity equals displacement over time, and velocity times time, v times t, is equal to the displacement. So displacement equals v times t. So the area underneath this is going to be equal to the displacement. In this case, we have to be careful because we have a triangle. So we're going to say that the area is equal to 1/2 the base times the height. I know that I keep repeating this, but it's essential to understand all 4 of these. The slope of a displacement time graph is velocity. The slope of a velocity time graph is acceleration. The area of an acceleration time graph is change in velocity. And the area of a velocity time graph is the displacement. So let's look at this sort of all at once. So we really only have 3 kinematics graphs that we need to understand. And whatever this is, it could be a line like this, a line like this, a line like this, a curved line, whatever. The slope informs us about the velocity. And the slope of a velocity time graph informs us about the acceleration. So the slope of a displacement time graph tells us about the velocity, and the slope of a velocity time graph tells us about the acceleration. Working backwards, the area of an acceleration time graph is equal to the change in velocity, and the area of a velocity time graph is equal to the displacement. In calculus, this idea of finding the slope is the instantaneous slope. This is the first derivative. And the slope of this would be the second derivative of a displacement, or the first derivative of velocity. And working backwards, these are integrals. You don't need to worry about this now, but that sets you up to help you to understand this concept if you go further with physics. Let's look at a real-life example. I have a Lamborghini Aventador, and let's say we put that Lamborghini Aventador at the 5-meter mark right here. So if we leave it there, it's parked, its velocity is 0. But what does that look like on a displacement time graph? Well, it's at 5 meters, that's its position, it's displaced 5 meters from 0, and that's not changing. So as time goes on, we have a displacement of 0. The slope of a displacement time graph is velocity. The slope of this line is 0, so the velocity is 0. And this makes sense, because what is a parked car doing? It's not moving. Now, the slope of a velocity time graph is the acceleration. The slope of this line is 0, so it's not accelerating. It's parked, so that makes sense. What are these graphs going to look like if we have our Lamborghini traveling at a constant velocity? So now our car is doing this. So as time goes on, it's covering equal amounts of distance with time. These are called dot diagrams. And if the spacing between the dots is equal for equal intervals of time, we know that the velocity is constant. If we take these dots and arrange them on the y-axis, and these are equal intervals of time, we get a graph that looks like this. Remember, on a displacement time graph, the slope of the line is the velocity. So what's the slope of this line? It's constant. So what does that tell us about the velocity of the car? The velocity of the car is constant. What is the slope of a distance time graph? It's velocity. So our velocity is constant, so v must be constant. So if this car was traveling at, let's say, 5 meters per second, then our velocity here would be 5 meters per second. Now, what's the slope of a velocity time graph? The slope of a velocity time graph is acceleration, and the slope of this line is 0. Well, if the slope of a velocity time graph line is 0, then the acceleration is 0. And that should make sense, because what's the car doing? It's not changing its velocity. It's not speeding up. It's not slowing down. So its acceleration is 0. Now let's work with our area. Remember that the area under an acceleration time graph is the change in velocity. There is no area underneath this line, so the change in velocity is 0. And that makes sense. It's not changing its velocity. But if we choose a time interval here and decide to find the area here using length times width or width times height, either way, that is going to tell us about the displacement. So that's going to be d, the displacement, or we would say the change in distance. What if we have a car that's speeding up? So let's say our Lamborghini is here at rest, so VI is 0. And as time goes on, it goes faster and faster and faster and faster and faster. In that case, it covers little bits of distance in the beginning. But as time goes on, because it's going faster, it covers greater amounts of distance. If we take these dots and align them on here, close dots that are spreading out, with equal amounts of time, that graph's going to look like this. It's going to be exponential. So let's look at what the slope is of a displacement time graph. The slope of a displacement time graph is velocity, and it starts out with a low slope, or actually a 0 slope, and then that slope is low, and then it starts to increase until it gets up here where the slope is very steep. So if it's constantly changing, if the slope is constantly increasing, then our velocity is constantly increasing. This slope informs this graph. Now, that should make sense, because what's the velocity doing? It's constantly getting faster. It's getting faster at a constant rate. What's the slope of a velocity time graph? The slope of a velocity time graph is acceleration. But this graph has a constant slope. Its steepness, if we went hiking, is constant. So therefore, the acceleration is constant. And that should make sense, because what's the car doing? It's going faster, 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 faster. And it's doing that constantly. Let's look at the area. The area under an acceleration time graph informs us about the change in velocity. So if we pick this area here, and we do that with length times width or width times height, that area tells us the change in velocity. The area under a velocity time graph tells us about the displacement. So if we pick a time interval in here, in this case we would do 1/2 base times the height, because it's a triangle, and that would tell us the displacement or the change in distance. This time, let's look at a car that is slowing down. Now, if the car is going to slow down, it has to have already been moving. So we're going to say that this car was moving at a kind of fast rate and then starts to slow down and stops. Okay, so again, it's already moving and then it starts to slow down. So if that's the case, in the beginning it covered lots of distance. And then as it slows, it covers less and less distance until these dots start to shrink. And again, if we put these dots onto the graph up here, we would see it look like this. So it would cover lots of displacement in the beginning. It would have lots of displacement in the beginning. And then it would start to get less steep. So the slope of this line in the beginning is large, so the velocity is large. And as the steepness gets less, the displacement time graph slope tells us about velocity, then the velocity decreases. And in fact, when this slope becomes 0, that's the point at which the car has stopped. So that would be right here. For an acceleration time graph, the slope of the velocity time graph is equal to the acceleration. This is a negative constant slope, so the acceleration is negative and constant. Now, what does that mean? If we call to the right positive and to the left negative, then our car has a positive velocity. It's in the positive zone here, but it's accelerating negatively because the force that's making it slow down is to the left. So our decreasing positive velocity has a negative constant acceleration. Free fall is when we throw or drop a ball in a gravitational field and there are no other forces acting on it besides gravity. So let's take, for example, a basketball, and we release it from rest, so its initial velocity is 0, and we let it fall down. Now, how's it going to fall? Well, there's a constant force on it, so it's going to accelerate. That's its net force. So it's going to go slow and faster and faster and faster. So in the initial part of the fall, it's not going fast, so it's not covering much distance. But as it goes faster, it covers more and more distance. Well, if we call down to be positive, then we can take this graph and flip it around and put it on our axis like this, and we can see that the graph is going to do that. Makes sense. Distance time graph, the slope is velocity, the slope is increasing, so the velocity is increasing. The velocity time graph slope is acceleration. This graph is constant, so acceleration is constant. Now, if this was on Earth, then the value of this line would be exactly 9.8 meters per second squared, which means that the slope of this line would be also 9.8 meters per second squared. Working backwards, the area of this graph would be the change in velocity, and the area of this graph would be the displacement. This is probably the most difficult of all the problems. A ball that is thrown up, reaches the top, and falls back down. So in this case, we're not dealing with the throw. So this doesn't include that part, the speeding up. It's already moving up. So we say start, slows down, stops, speeds up, speeds up, speeds up. So what is it doing? It's moving fast, and it's slowing down, slowing down, slowing down, slowing down, stop, speeding up, speeding up, speeding up, speeding up. In other words, it's doing that. So if we call down to be negative, in this case, it has a positive velocity to start, and it's moving fast, so the line is steep. But as it slows down, the slope of this line, which is velocity, must decrease. And eventually, it reaches 0. And at the tippity top, that's where the slope of the line is 0, so the velocity is 0. Then it starts to fall back down, and this is where it's tricky. The slope of the line is increasing, but it's negative. So it is speeding up in the downward direction. Let's take a look at what that looks like on the velocity graph. The line is steep and positive, so it starts here, and the slope is getting less. It's decreasing, so the velocity is decreasing, and eventually it gets to the point where the velocity is 0. Then it starts to speed up in the negative direction. So its velocity in this part of the graph is actually increasing, and the negative part of this graph just simply means that it's now moving down. So the plus was the upward part of the trip, with the velocity being positive, and the downward part of the trip just means it's moving down and has a negative velocity. Interestingly enough, the slope of this line is constant, whether it's moving up, whether it's at 0, or whether it's moving down. A constant slope means a constant acceleration, and this value right here is actually going to be negative 9.8 meters per second squared on Earth if we call down to be negative. One last item that we have to be careful of: the difference between distance on a graph and displacement. Remember that distance is defined as the total path traveled. So in this case, the object moved, let's say a person walking, they walked 10 meters and they turned around and walked back to the 6-meter mark. So how far did they go? They traveled 10 meters forward, and then they moved 4 meters back. Their total path in that case would be 14 meters. But remember that displacement is defined as the straight line distance from start to finish. So they start here and they end here. What did they do? They went 6 meters forward, and that would be plus 6 meters.